Hi, today another famous problem, which is search a list of integers sorted in ascending order, and basically find if a number x exists in this list and return its index. If it exists, if it is not, return -1. So basically we should use binary search here. It is most efficient because every time with binary search, we basically every time we are trying to divide list in half, and the time complexity in this case is log base 2. We call log base 2, and this space complexity, well, it depends what do we do. If it is the iterative way, we can do constant. If it is recursive way, we can do basically also log base 2 space complexity, but we will do the most efficient iterative way. Basically, to visualize the solution, you need to understand that how binary search works. So you need to do iteration where every time you pick a middle point, a so-called pivot in your list, and you check if this pivot is less or greater than the target number x. So if it is less, you just slice your array. You're interested only in the right side of array. If it is greater than your target number x, then you need to look to in the left side of array. I will show you how it works. Okay, so to do it, we need two indices. In this index I on we need two variables, I index 0 and j is basically length of our array. Okay, and -1. Okay, and then we loop while I less equal than g. Okay, we always calculating middle value. It can be I plus g divided by 2. Okay, so if nums mid is equal to x, we just return this index. Else, if nums mid is less than x, we just want to increment I equal to mid plus 1. Else we need to decrement j, which is mid -1, and in the end we just return -1. Basically, if we we exited the loop and we haven't found haven't found the mid, we return -1. It means that the target x doesn't exist in the array. Okay, execute. You see basically all our test cases here we pass true. And yeah, let's look. Now it's interesting to see how it looks while debugging all this. And yeah, basically let's pick only one test case with 7. Okay, we are here. We defined variable I and j. So we are here I at index 0, j index 7. Okay, now we are looping while I is less equal than j. So mid now is 3, and we check what is on the index 3. We have 3 on the index 3. What consonants? Okay, so basically, is 3 equal to x? No, it is not. 3 is less. So we don't care about all these numbers anymore to the left at all, including a number on the index 3. We are looking only on the right, so we can increment I to 4. And we do it here. You see I is equal 4, j is equal 7. And now on the next iteration we look on this slice. You see how fast it can go if you have enormous array. You just slice array in 2 and you don't care about half of the array. And you continue with this. You do it also with another slice. In another slice we do also slice only half and continue until we found either we find our target or we exit the loop normally. We haven't found nothing and we should return -1. Okay, but here we have our target 7, so let's continue. And you see a new mid calculated is equal to 5. And what do we have on the index 5? On the index 5 we have 7, and it is equal to 7 x 7, so it is what we're looking for. Thus we just return our index 5. That's it. We have our result. Good. So that's it. Again, the time complexity here is log n base 2, and log n we can write log n just because in the software engineering log is always base 2. In math it is, if you write without base, it is base 10, but in computer science it's always base 2. Yeah, and space complexity here is 1 because we don't allocate any extra space. Yeah, the solution is iterative. Good. That's it. Thanks for today. Have a nice day.